Alright, so in this video we're going to talk about gravity again. And gravity, we've been talking about it since the beginning of the year. And we started by talking about little g, which is acceleration due to gravity. Okay, and remember these words due to gravity, we kind of clarified when we got to the unit on forces, like what that means. So little g is acceleration, which is 10 meters per second squared. Then we began talking about forces, and we learned that when you apply force to an object of a certain mass, it causes that mass to accelerate. So little fg now became our force due to gravity. Again, so this idea of due to gravity is still in the statement there. And the unit is in newtons. And it doesn't have a set value like this, but it's equal to the mass times the little acceleration due to gravity. Okay. We also, just as a reminder, remember this is what your weight is. Alright, so when we looked at an object, let's say we had a box on a table, and we were applying a force to that object, and let's just say there was some friction, it was accelerating to the right. We drew a free body diagram. We would have an applied force for us pushing on the box. We'd have the friction for the box rubbing on the ground. You'd have normal force for the table pushing back up on the box. And then we had force due to gravity. Right? Now, if you think about it, when you look at all of these forces, in every single one of these cases, these forces are caused by something touching the box. So I always said when you did your free body diagrams, think about what's actually pushing or pulling on the box. What's touching the box? Only a force can be applied when something's touching it. And the exception was the force due to gravity. I just said that's always happening. All right, so now we're going to talk about why that's always happening. So this is the law of universal gravitation. And it states that an attractive force exists between all objects in the universe, and that it is directly proportional to the masses. It is directly proportional to their masses and inversely proportional to their distances. We'll say distances between the centers of mass. And I'll talk about what that means in a second. Right? So that's the universal gravitation in words. Let's go ahead and look at it mathematically. So it says we have an attractive force. There's a force due to gravity that is directly proportional to their masses. So two objects is between two objects. So we'd have two masses, and this would be on the top of the fraction because we're multiplying them. So that means if this were to double, this were to double, so directly proportional. And it's inversely proportional to the distances between the center of masses. And it's actually to the square, sorry, I missed that, of the distances between their center of masses, which we write with an R, and we would square it. So what this means is, let's say we were to double the radius while it's on the bottom, or the distances, it's on the bottom of the fraction here, so that would make the bottom of your fraction 4 times as big, and so it would make your force 1/4 as big. If we were to 1/2 the distance, then it would quadruple the force. And if you think about this, this is similar to magnets. It's actually exactly like magnets, because that is also an inverse square law, which is also a field force, which is what we call these forces that exist without contact. Where if you bring two magnets really close together, they're going to pull on each other. The force is going to be stronger. Or if you pull them apart, the force is very weak. Okay? Now, one of the differences between electricity, magnetism, and gravitation is gravitation is always attractive, whereas electricity and magnetism can also be repulsive. Now, my equation is not complete here because after performing lots of calculations, a mathematician, Henry Cavendish, actually determined that in order to quantify force in terms of newtons, there's actually a constant in this equation. And the value for that constant is 6.67 times 10 to the negative 11th. It's the universal gravitation constant. And the unit for it, it's a big mess because you're trying to cancel out these things and make it so it's in newtons. So you have newtons on top. You have meters squared here on the bottom, so you'd have to have meters squared on the top of this unit, so that would get that to cancel. And then you have kilograms squared up here, so you'd have to have kilograms squared on the bottom to get that to cancel, so you'd end up with a unit of newtons. All right? Now I kind of want to look at what this means sort of conceptually and derive a couple other equations that are going to be useful based on this and stuff we already know. Right? So let's say I have the Earth. Okay? And on the surface of the Earth, I have, a person. And then out here, I have like a tiny little satellite that's going around the outside. Right? So let's go ahead and look at what this means here. If we were to have our force due to gravity, right, we would have a gravitational constant times, so we would have the mass of the Earth, and then we'd have the mass of the person over, and this is one of the instances where we look at this and we'd see, okay, well, the distance between their center of masses. Well, a person is so relatively small that their center of mass is negligible to that of the Earth. So in this case, the radius of the Earth is equal to the r that's on the bottom, right? So we would have our r squared. Now, if I were to have a very large object, and I have no idea, I don't know, let's say this giant asteroid was out here, it's like a third the size of the Earth or something. Now we have a radius that would not be negligible. So you've always got to sort of think in the problem whether or not you need to add in this radius, or if the radius of one of the objects is negligible, or even if we were talking about like the sun way over here, the sun is so relatively far away that really like the distance between the Earth and the sun is so big that neither the radius of the sun or the Earth matters. So you just kind of have to look at the numbers in the scientific notation and what's meaningful and what's not. All right. So let's now look at this person and figure out, well, what is their acceleration due to gravity? Right? How did we get that number? Where did that 10 come from? Well, if we use our new equation that we have here, as well as our old equation that the weight of a person is equal to the mass of that person times the acceleration due to gravity they're experiencing, we can see how we can actually quantify acceleration due to gravity on different planets. Right? So we're going to plug this in for here. So we get the mass of the person times gravity is equal to this big constant times the mass of the Earth times the mass of the person all over the radius squared. Okay. So if we cancel the mass of the person, we can see that gravity on the surface, so the acceleration due to gravity on the surface of the planet, it's relative to how massive that planet is, and the radius of the planet squared, or inversely proportional to the radius of the planet squared. Right? So we know, and this also proves the whole idea that mass does not affect g. So everything on the planet drops at the same rate. Now the other thing I want to look at is the idea of orbital velocity. And this will be the last thing in this video. So we have a satellite, right? And it's going around the outside of the planet, so it's going to have some tangential velocity in this direction, but it's going to be circling around. And so this entire unit we've been talking about circular motion and the fact that centripetal forces cause objects to turn around other objects. So if this satellite has some velocity here, but it's circling around, then there must be some force towards the center of the circle. And in all cases, we've been looking at the idea of what's causing something to turn. So the centripetal force is like the F net of what's causing this thing to turn. And in this case, the F net is actually gravity. So we get that we're going to combine two equations here, that the centripetal force acting on the satellite would be the mass of the satellite, v squared over r, okay, or its radius of orbit. And we also have that the force due to gravity between the satellite and the Earth is equivalent to that. And that Fg is actually what's causing this Fc. So these two would be equivalent to each other, right? So I'm going to just write that down here. We have some force due to gravity between the satellite and the Earth, all over r squared, that is equal to or causing the centripetal force of the satellite moving at some velocity at some radius. And remember that this mass is always the mass of the thing that's turning, right? So let's look at how this can, how we can solve this for velocity. So I get the mass of the satellites cancel, I get one of the r's cancel, and so I essentially get that orbital velocity is equal to the gravitational constant times the mass of the Earth, or whatever is being orbited around, all over, so this is only canceling that square there, r, and that's squared, so we'd have to take the square root of this. Alright, so using previous ideas now with our new universal gravitation equation will allow us to calculate some different variables in terms of objects or larger massive objects moving in the universe.